Hey class, here's a video to help you all out with problem number 24 from the homework. So, what you see here, I've broken our picture down, or our problem down, into 4 separate instances. In instance 1, or picture 1 here, you see the block is at rest starting at its top maximum height h. Okay, so I'll just label h in here. So this here is h, the height that it starts from relative to where the block and the bullet make contact with one another. So we'll call that h. Here in picture 2, you can see the block is just about to contact the bullet the moment right before, so both the bullet and the block are moving. The block, as you can see, is moving in the downward direction, while the bullet is moving in the upward direction. And the velocity of the bullet is given to you as some number. Everybody's number is slightly different, but it is a given. Then you can see over here that in picture 3, the bullet and the block have now become adjoined because the bullet has embedded itself into the block, and you can see both of them are now moving together with an upward velocity, and again that's a value we do not know. And then here at point 4, the bullet and the block have now returned to the exact same height h from picture 1, and they together are now at rest with a velocity of 0. So a key thing to keep in mind and to acknowledge is that these h values are the same from picture 1 and picture 4. So in trying to solve this problem, you look at it at first and it might seem pretty tricky, especially since it's asking us to determine what the time is that it takes for the bullet to, or the bullet and the block together to reach back to its original height, which will be actually, as we'll find out, is going to be the same time that it takes the original block to fall down to the point of contact. And the reason that we know that the time is the same from picture 1 and from picture 4 is actually because of symmetry with projectile motion, things that we learned back in chapters 2 and 3. It should take the same time for anything under free fall if we ignore air resistance to travel the same distance. So if we go ahead and look at this, we can try to figure out what the velocities are and hopefully use those to find the time. So if you want to consider looking at the impact between the bullet and the block, we're going to look at locations 2 to location 3 because that's when they impact one another. And during the impact between positions 2 and 3, we're going to use the concept of conservation of momentum. And the reason that we use conservation of momentum is because there's an inelastic collision occurring, and when there's an inelastic collision, energy is lost, so we cannot use the idea of conservation of energy. So conservation of momentum tells us that the initial momentum is going to be equal to the final momentum. So in this case, then, what we're going to have is that both the block and the bullet are moving initially, so you're going to have the mass of the wood block multiplied by this V2 value that we don't know, plus the mass of the bullet multiplied by the initial velocity of the bullet. That's your total initial momentum, and that is then going to have to be equal to the final momentum, which is going to be when the two stick together. So it's going to be the mass of the wood plus the mass of the bullet multiplied by their combined velocity v3 when the two of them stick together. So this looks fine and good, but I don't see time in this equation at all, right? So you wonder, how can you use this to solve for time? And that's an excellent question. And in order to do that, you're going to have to try to look at what's going on at points 1 and points 4. Okay, so if we consider point 1, for example, if we consider point 1, well, really the transition from 1 to 2 to be more specific, we have an object that's in free fall, so we can actually use our equations of motion to figure out what that velocity 2 is going to be, because what it tells us, if we remember back to our equations of motion, we know that the final velocity, in this case velocity 2, for an object is going to be equal to its initial velocity, velocity 1, plus acceleration multiplied by time. So what that means is that velocity 2 is going to be equal to, since velocity 1 is 0, it's just going to be equal to negative g times time. And it makes sense that it's negative since we know it is moving in the downward direction. And so this v2 is really the blue v2 from earlier. So we now know what v2 is in terms of time. That's nice since that's what we're trying to solve for. So it can be plugged in up here. And similarly, you can use equations of motion and analyze what happens from point 3 to point 4. And you can actually use the same equation of motion, but in this equation it's going to tell us that v4 equals v3 plus acceleration times time. And once again, we have a value of 0 in this case for v4, and so what that tells us then is 0 is going to be equal to v3 minus gravity times time, and so you can observe that v3 is equal to gravity times time. So this time here, the time it takes to go up from 3 to 4 because of symmetry, is the same as this time here that it takes to go from 1 to 2. And since those two times are the same, and it's that t that we're trying to look for, you should be able to plug in our equation for v3 here and our equation for v2 into the equation of conservation of momentum and be able to solve, hopefully, for the time. So go ahead, give that a shot, let me know if you have any questions, and I hope that is helpful. Have a great day.